Thank you. Good morning. I started with returning the homework. So since there are 100 students in the class, it has to take a very short time. If it takes 10 seconds each student, how much we are going to lose for returning 100 homework? Right, 15 minutes. So we can't afford it. It has to take a few seconds per student. So I need your cooperation. So we do it this way. I read the name, and then I have to hear yes or no, or here or nothing. If I hear it, I put it here, you walk and you pick it up. If I don't hear, I put it in a pile that goes to the PA. So if you have your homework here and you want to pick it up, you have to speak loud enough that I hear that you are coming. If you cannot speak loud enough, come here now, and when your comes, you touch me, and I'll give it to you. Good enough? Will we give it a try? Okay, Kobe. A little bit louder, thank you. Connor, Kate. Bennett? Here. Thank you. Jarvin? On my way. Thank you. Janosh or something similar? 8. Tristan? Here. Yogi? Alec? Moore? Basel, Minglian, Frank, San, Andrew Gonzalez, Benjamin B. Here. Jeremiah P. Here. Sanjay K. Here. Poonam R. Here. Hannah F. Oh, we are doing this beautiful. David Gilmore. Here. Annie Ruth. Here. Ronnie Song. Faisal A. Here. Lee here. Here. Lee here. David A. Spencer and Adam Little, Abdullah A. Here. Dwaniel. Here. Keith M. Here. Dennis M. Boxerman Zhang. Seunjung, Victor T. Carl McCullough, Cody W. Daniel P. Here. Sam V. Sam Brock. Austin Sheen, Shia, Jason Young, here. Ray Emery, here. David Ross, here. Sunat S. No. So, okay. So let's not mess around with it. Then we give something to the front here. Is that yours? So you get it from the DA. Let's do this. Let's not stop it this here because we lost a lot of time. Buxian Su, Alright, it doesn't matter. You will do great. Carson Cook.
Here.
Andy Veruca. No. I don't know. James Graham.
Here.
Rodin P. Alright, so why let me hear you. Jacob Collins.
Here.
Joe Sester.
Here.
Robert Longacre. Jamal and Lee Hong.
Here.
Morgan K.
Here.
Jeffrey Beto.
Here.
Cameron N. Andrew Wyatt. Wei Wei Chen. Tapisa Wood. Ramit D. William Newcomb. All right. All right. Homework. Do I have the homework? All right. If you have the homework, bring it here, please. Thank you. All right, schedule. So on Wednesday we had the meter. The meter has everything up to relations here because we finished last week. And today we start with we started with algorithm last lecture, but we didn't do very much. So just as a reminder, you need to bring a Scantron form. The link was broken. Someone pointed out. Thank you. This is the Scantron form that you need. It has a form number 882-E. Thank you. I fix a few. So let me see. So I'm not online. So if it is still broken, please send me an email, which one you mean, and I'll fix it. There were a couple broken, and I think I fixed everything, but it's hard to tell. If something is not right with the website, send me an email and I'll fix it very quickly. Thank you. So any question about the exam? The exam will be 33 questions like the one you do for homework. You have to make the choice. You don't have to write any justification because it's going to be graded by a machine. And you get 1 point for each correct answer and 0 if the answer is wrong or you don't answer. Some questions may have 2 or more correct answers. Like I ask you a function, I say, is this function injective or is this function bijective? So if the function is bijective, the correct answer is bijective because it gives you more information than injective, even though injective is right. You get a 3 critic. If a question may be wrong, poorly phrased, may have typos, it happens. And so you get a discount of 3 wrong answers, possibly for this reason. There are not going to be 3 wrong questions. So you are away in the game. I don't answer questions during the exam for your benefit. Because if in the middle of the exam I answer a question that makes you understand the question in a different way and you already answered, or you already have left the exam, then it's not fair. So, at least we all play with the same rule and with the same advantage already. Think someone had a question there? No.
Can you just remind us what the exam covers?
Yes, I think I just did it, but that's fine. 1 and 2, section 1 and section 2 that we cover here. There is a link to readings. So in the link to readings, you see exactly, let me find it here, readings. And here there is each section of the book or the notes that we cover. So is all the stuff from here up. Good question. Anything else? Yes?
It's going to be a 30-point total because of the 3 freebies?
Yes. Yes. 33 question and it's scaled to 30. Anything else? Yes?
How long is the exam?
66 minutes, 2 minutes per question. And it's really intended that you do it comfortably. Unless you want to brute force some question. And so then it's going to take forever, but this is not a big deal. Anything else? So before we move on, is there anything about this homework that you want to discuss, the one that you just turned in? Or about the material we covered so far? Something to review? Yes? 10 and 11 on the homework. Fantastic. All right, question 10. First, I define here a relation, binary relation on n cross n. Should we, as we usually do, which is a good thing to do, should we write a few pairs that are in the relation and a few that are not to make sure that we understand it? Who want to tell me a few pairs that are in this relation? The relation is defined in this way. X is related to y if and only if x is a factor of y. X is a factor of y. All right? So some pairs in this relation. 2, 2. Very good.
1, 2.
1, 2. Some other. 2, 4. Some pairs which are not in this relation. 5, 7. 3, 5. 6, 6. 6, 8. All right. So we got it, right? The first one has to be a factor of the second. Now, what are the questions? Is this reflexive? Is this a transitive? Is both or is neither? Is this reflexive?
Yes.
Yes. Why? Fantastic. So, yes, reflexive. Is this transitive?
Yes.
Yes. Why? What you said is right. I don't think it's a good example. Yes?
If x divides y and y divides z, then x divides z.
Yes. If x divides y, means that there's a even number of times there, no reminder. And then y does it for z, then x also does it for z. Right? Let's make an example. 3 and 9 are here because 3 divides 9, right? Then 9 divides 18, and so 3 divides 18. Why? Well, because if you take 18, 18 is twice 9, and this one is 3 times, so you have 6 times there, right? So it's reflexive. And so let's go back to this one. And so the correct answer is all of the above, because it's transitive and reflexive. Yes? I'm sorry.
Does the domain include zero? Since it's natural.
Yes.
And if it does, is it still reflexive? Because zero is not a factor of zero.
Well, why 0 is not a factor of 0?
Because it's undefined.
What is undefined?
You cannot divide anything by zero.
I'm not dividing here. Factor means that, so when do we say that x is a factor of y? X is a factor of y if there exists a t such that xt is equal y, right? Factor. We say that x is a factor of y if there is, oops, you are not seeing, I wrote it here. I say that x is a factor of y if there exists a t such that xt is equal to 1. Yeah? Sounds good?
I mean, I would assume that x is a factor of y if y by x is an integer.
If y by x,
Is an integer. If you divide y by x, you get an integer.
well, maybe here. So, all right. So I think you understood the well. Now we have to argue what does it mean x factor of y, right? So I give this definition. X is a factor of y if there exists a t such that when you multiply this, right? These are the two factors of y. This is how we say it means, right? If I tell you the number 6, what are the factors of 6? Will you tell me 2 and 3? All right, so I think you understood. And actually you understood very well, because say, if 0 is there and I cannot divide by 0, then it's not reflexive. Excellent, fantastic. You understand very well reflexive. All right, any other question? Yes? I'm sorry? Number 8, so I'm still trying to satisfy 11. 11. All right, this is a relation on N60. We have defined N60. Who wants to tell me what is N60? Zero, 1, 2, up to 59. Right? Yes. Up to 59. And we also said when you write it that way, we do addition, multiplication, subtraction, whatever, mod 60, typically. All right, so we have this one. And we say that two elements here are related if the leftmost digit of the decimal representation is the same. So who can tell me two numbers which are related?
1 and 11.
1 and 11, fantastic. So 1 and 11 are in this relation. Another one? 2 and 29. Leftmost digit, yes. 2 and 29. All right. I was thinking the other left. All right. Who wants to tell me some pairs which are not here?
50 and 40.
50 and 40. Some other.
60 and 40. Oh.
60 and 40. Yes, it's pretty good. All right, so we got it. So now we want the equivalence classes, right? So what is an equivalence class of a number, of an element there?
Partition?
Say that again?
Partition?
Partition? No. An equivalence class is a subset of that that contains all the elements equivalent to each other. So let's say that I want the equivalent class of 4. The equivalence class of 4. What are the, sometimes we write it in this way. What are the elements in this equivalent class? All the elements that are equivalent to this. So we have the 4, 40, 41, up to 49. Very good. What are the equivalent classes of 0? 0 by itself. Very sad. What is the equivalent class of 6? 6 by itself. Equivalent class of 3. 3, 30, 31, up to 39. All right. So how many of these different there are? 10. Very good. We also know, because we discussed it, that if you do the intersection of these two, the intersection is n. And we also know that if you take all this and you put all of them together, you get back n60. And so we call this a partition. Someone mentioned the word partition, right? So all these sets will be a partition of n60. Partition under that equivalence. We could have other equivalences. All right. Good enough? I'll do 8 and then I'll move on. All right. Yes. 8. Who asked me 8? Yes. Oh, you don't see. All right. 8. So what do I have there? Let's read it. I mean, this is 2 lines. First, let's see that we understand the question. I define 2 binary relations, R and S, and then I pick some pairs and I ask you whether they are there, which is what we typically do. All right, so should we understand these 2 relations first?
Because one is equality and the other is greater than.
Yeah, does it offend you? So we have 2 relations, right? Both are on n, binary relation of n. So the pairs are elements of n. And we can do anything we want. We could say one is greater than and the other one is a factor, because this was one of the relations. Or we could say the other one, they start with the same digit. The leftmost digit is the same. We can make relations any way we want. So who want to tell me a few elements that are in R? We want the first element to be greater than the second plus 2, right? And so in R we have 5, 2. Why? Because 5 is greater than 2 plus 2. Thank you. Who wants to tell me another pair? 7, 2. Right. Why? Because 7 is greater than 2 plus 2. Can I put another one here, there? 9 and 1. Why? Because 9 is greater than 1 plus 2. We want to put a 1 that is not here. Someone said 1, 1, which is correct. Why? Because 1 is not greater than 1 plus 2. All right, so we have a better relation there. let's write S. Some elements in S. So X has to be equal Y take away 2. And so what do I put here? 2 and 4. Yes?
5, 7.
Say that again?
5, 7.
5, 7. One that is not here? 1, 1 again. Yes? Alright, so now I'll give you a pair, and the pair that I give you is 5, 2. And I ask you, is this one, question mark, an element of R composed to S? So what is supposed to happen? I have to understand the composition, right? So I will explain this on this example. I can say that 5, 2 is here if and only if there exists some Z such that 5Z is in S and Z2 is in R. Yes? So I'm trying to answer this question. Is 5, 2 in the composition? So if I can find this Z such that 5Z is in S and Z2 is in R. This is the definition. There is really nothing except remembering and understanding what this one is. So, can I find this Z or not?
Yes.
Yes. What would it be?
7.
And then
7.
7. Oh, you are quick. So, let's see. 5, 7 has to be in S. Yes, because 5 plus 2 or 7 minus 2 is 5. Very good. And 7, 2 has to be in R. Yes, 7 is greater than 2 plus 2. Fantastic. So, 5, 2 is in the composition. And the other one is 5, 0 there. And so, to answer whether 5, 0 is in R S, I need this one, so I need 5Z in S and Z 0 in R. You with me? So to have a Z 0 in R, what do you need? Who can tell me a Z such that a Z 0 is in R? I'm sorry?
Any number greater than 2.
Any number greater than 2. And what about the 5 0 in S? Has to be only 7, right? And so this also is in the derivation, right? No? Sorry, writing all this, So, we have to define, let me start again. We have to find whether 5, 0 is in the composition. And so, we want 5Z in S, and S is so this has to be a 7. There are no other options. So is a 7 0 in R? Yes, because a 7 is greater than 0 plus 2. All right. So both are in there. All right. Enough. I think this was a good review. Of course, if you want to know more, you can go to the TA and he will go over any problem you want. Yes? Was there a question?
I don't know question 9, but
All right. You go from the TA, he will be happy to do it. Yes?
So the way composition works is that you would basically, I guess, sort of like S
Yes, and when we write it in this way, first we do S and then we do R. And I think I mentioned in class that some authors do the opposite. So in this class, because we use this book, first we do S and then we do R. Yes?
You could also combine the two functions and then just plug in X.
Two functions.
Well,
Yes, you can combine the function exactly as you combine the relation.
I see.
Actually, it's easier because function you have only one value. Yes. All right. Let's move on to algorithm. I think it will be a fun lecture. So last time we briefly said what is an algorithm. And we started to talk about a recursive algorithm. So let me briefly say again what is an algorithm. It's a sequence of executable steps. There is no mystery in the step. This is something that is easy to see and understand and do. The execution has to be finite. We must know that the execution terminates. Is deterministic. So when you do a step, you have only one output. You cannot have two. You cannot flip a coin. And you have input and output. Often in algorithm also we make a function or subroutine or method or procedure call. And the steps that we do are assignment, if then else, while, and input output. Then we look at a couple of recursive algorithms. Yes?
I have a question about the notation for the an plus 1.
Yes?
Is there a reason that it's not an equals a times a to the n minus 1?
Yes. Because if I say an plus 1 and we know that an is a natural number, this can't be 0. But if you say a0 and n could be 0, right? But then when you do the minus 1, you go in the negative that we don't have.
So plus 1 makes sure that it's
Right. That is, yes, very good question. All right, so I want to code this one, not now, but maybe by the end of this lecture or maybe next week. You remember that initially we spoke about the coin change problem? So here I want to write a program, and you may start to think about it, that if I give you the change, will give you all the possible coins that make up of that change. So if the change is 10 cents, you can have a dime, or you can have 2 nickels, or you can have 10 pennies, or you can have 1 nickel and 5 pennies. Right, I want to compute all these possibilities. And so this is an example where if you don't use recursion, you are going to make your life incredibly difficult. You may try to do it with the for or with the while, and then I do it with recursion, and 2 lines and the thing will be done. But I'm going to do this later, all right? So now I talk about complexity. Why complexity comes about? When we talk about function, we have this idea of a black box where something goes in on one side and something else comes out on the other side. And jokingly, I told you, look, there are little green men inside with crank and polish. and they do all this, and the results come out. When you have to do things in practice, you have to know what these drag and pulleys are, and how many times you have to turn it. If you have to turn it so many times that is the age of the universe, you can't compute with those things, right? And indeed, there are problems that is going to take a million or billion or trillion of years to compute, even if we can write the problem in a couple of months. And so now we want to discuss how difficult, how computationally difficult or intensive it is to compute something. And then we will discuss some algorithms that do that. So, what is the complexity? The complexity is a function, and now we know everything about the function, right? So the complexity of an algorithm is a function that takes the size of the problem that you want to compute, the size, all right? So suppose that I have an array of numbers, and I want to know whether the number 37 is in this array. If you have an array of 3 elements, you look the first, the second, and the third, you are done. No big deal, right? If you have an array of 3 million elements, you by yourself, you cannot do it. You need a computer because you cannot look at 3 million elements. It's going to take a year, right? And so, the same problem, if the input is bigger, is a difficult problem. If the input is smaller, is an easier problem. So we have a function that takes how big is this problem that you want to solve. We call it size of the problem. Similar is to multiply numbers. When you do encryption, very often you multiply 2 numbers. These are not small numbers. So these are numbers that have 300 or 1,000 digits. Obviously, when you have to do this one, you cannot do it with the hardware. You have to write a program that sees all the digits one after another. And so the more digits you have, obviously, the more it's going to take to multiply this number. Right? So, depending on the problem, we have to look ahead and see, well, if I write an algorithm, the size of the input is this. If you multiply numbers, the number of digits. If you are looking for something in an array, is how many elements you have in an array. If you sort, it's the same. Clearly, to sort a bunch of numbers, the more number you have, the longer it takes. So the complexity is a function that takes the size of the problem as input and is telling you how many times one operation of your algorithm is going to be executed. So again, if we look for one element in an array, what is a significant operation that is going to be executed? Compare the value you have with the element at some index in the array. And then you do for the next index, and for the next index, and for the next index. And so you have to pick an operation that makes sense. And so this requires a little bit of creativity, a little bit of art and experience. It's like writing a program. If I ask you to write a program for something, I don't have a recipe. You have to be creative. Actually, this is why once you get a degree, you are going to work for a company and make a lot of money. Because you need this kind of skill and creativity. And here it's simpler. And so here we have a notation, big O, which is the one that is going to express the complexity of this algorithm. And we write it there, and then I start to make examples. We say that the function f of n is big O of g of n, and we typically write it in this way. We write f of n is equal big O of g of n. Yes, thank you. So this symbol here is a disgrace. Very misleading. And why people do and pronounce it that way, I really don't have a good excuse for that. It's tradition. O of g of n is a set of functions. A set of functions. And now we are going to understand which functions are in the set. That notation means that f of n is an element of that set. So a good notation for this one would be this sign. And a good way to put it would be f of n belongs to big O of g of n. But we write it in that way and we say f of n is big O of g of n. And so when do we say this? When do we say this one? It says, look, let me take f of n. I'll take the absolute value. In our case, this function will always be positive. So, just to make it easy, don't focus so much on the absolute value. If this one is less than c g of n, where this is some arbitrary constant. Thank you. Arbitrary means that you can pick anything you want. And this is true when, for n greater than or equal, it doesn't really matter, some threshold that I call m. So we have to find this c and this m. If they exist, we say that f of n is big O of g of n. You with me? So let's take an f and let's take a g and see how it works. So first I want to show that n is big O of 2n. So how do I convince you that this is true? Well, let me find a g and an n such that that condition is satisfied. N is less than what? 1 times 2n for n greater than or equal to 0. You with me? This is this n. This is the 2n. This is the c. And this is the m. All right? So because this satisfies that formula there, I can say this one. So what's good? So let me flip it now. Let me flip it and I'll ask you to do it. I want to see that 2n is big O of n. And you just more or less copy from what I did the line ago. So what you have to do here, 2n has to be less than, we also put the equal here, some c times n for n greater or equal to m. So what is this c? And what is this m? Right, you have to find one. So c is equal to 2 and m is equal to 0. And so we also prove the other one. When this happens, we say that f of n grows no faster than g of n. Why? Because the faster the threshold, the faster this n, f of n is always below g of n when I use that constant. Yes?
So it's like the worst case scenario, like as long as it will ever take.
Yes. What is that C? The intuition. The intuition is that when you want to do these things, and these are really computation times, well, C means that you have a 8-core machine rather than the 2-core machine. Or you have a clock which is 10 times faster. Or something like that. And so these are constant, and we sweep them under the rug with this C. What is the meaning of this n? That if the problem is small, the size of the problem is small, we don't care. A small problem, and we can solve it anyway, is when the numbers get bigger, the problem gets bigger and bigger and bigger, that then we are in trouble. All right, does someone have a question?
I was just going to clarify that C is like the time to execute each n.
Well, yes and no. I mean, this is a definition, but some intuition is correct. Yes. So, let me go back here. So this function that takes the size of the input and return the number of times that some step is executed is called a running time. The name couldn't be more misleading. Because first, we don't measure time. We measure the number of times that some step is executed. We don't look at the clock. Second, we don't run anything. This is just a function that relates one thing to the other. So far so good? So, let's see a couple of examples of this big O notation, a little bit more difficult, a little bit more complicated. So, let's show that 2n plus 3 is O of n. Yes? So here we have to prove what? We have to prove that 2n plus 3 is less than or equal c times n for n greater than or equal m. And here I want to know what is this c and what is this n. Of course, if you take a million and a million, it's going to work, right? The point is that I want to get something which is sensible, so I understand why and how. Yes? All right. How do we get there? Or you just write and you get a sense that this works?
You determine basically constant addition plus 3. How? So you want to take 3 and be larger than 2n, but only when that increment of 1 over n is equal to or greater than.
Yeah. So, let me do in one way and you tell me if it matches yours, or but your I think is correct. So here I have 2n plus 3, right? I have to show that this is smaller of something else. So I say, look, this is smaller or equal to 2n plus n when for n greater than or equal 3. Right? When n is 3, I have 2 times 3 plus 3 less than 2 times 3 plus 3. Right? If n is bigger, the 2n and the 2n on both sides is the same, but in one side I have 3, in the other I have something bigger, so this is okay. You with me so far?
No, because what, how do you know that this side of it, okay, what is this 2a plus a? So what?
No, I invent,
Okay.
because I'm very smart. Alright? Alright. So, now, I say that this is less than or equal, and here I say actually equal, of 3n, right? Yeah? And so now this is my C. 3 is my C. Because I have what? This is this n, this is a C, and this is n. All right? And so you were right, and this is a proof that you were right. Are people with me? No? So I want to show that this one is less than C times n. And I have to find the C. So I said, look, this 3, I don't know what to do this 3. Let me replace with n. When I'm okay replacing it? Well, when n is greater than or equal than 3. And so this one is 3n. All of a sudden I have this Cn that I wanted to find here. Yeah?
What's your explanation of n again? Just like in English?
This n, so the n is the threshold. When I want to show that f of n is less than or equal g of n, beside the constant, I don't care for small numbers. I don't care for small problems. I really care for big problems. And big problems means n greater than this number. All right? So before we break, let me consider this one. N squared equal O of n. And I put a question mark. Is it or is it not? So, to answer yes here, what is supposed to happen? What is supposed to happen is that n squared is less than or equal C times n. For n greater than or equal some m, right? Yeah? So, for n greater than 0, this becomes what? N greater than or equal C. Yes, thank you. Right, I simplify n on both sides. So C should be a constant that is greater than every n. Of course you don't find it. No matter what you see, C plus 1 is greater than C. So cannot be greater than every n. This would be the biggest number of all. And so what I conclude, that I can never solve n squared less than or equal Cn. And so I concluded that n squared is not big O of n. All right? Ready for a break? All right.